recording on this computer. Lovely. Okay, fantastic. So during previous lecture, we looked at the case when we had a Mach-Zehnder interferometer, and from Mach-Zehnder interferometer, what we drive, we found out that looking at only one port and looking at the intensity or irradiance there, what we can get interference effect, which this interference effect is given by the correlation between the two fields. So the correlation that I found last time was some sort of like some sort of this form, which is I think first I went, did I normalize it? Yes, I think I did the normalization as well. So it was G1 of R1 and T1 and R2 and T2, which R1 and R2, they can be R up and R down, the path that the two beams is passing through. And that was given by average of E minus R1 T1 E plus of R2 and T2 divided by the average.
I cannot see you writing on the screen.
Oh yeah, okay. Live broadcasting to Zoom has stopped. YouTube, you have stopped the screen sharing? No. Okay. Huh. It has some issues. Zoom has an issue. I will pause. Okay, you should have it now. Sorry, guys. These sort of things happen in online courses. Oh, yeah. I was writing, guys. So I will encourage you to turn on your videos without don't turn it off, okay? Because I may see your reactions. Okay, so, and then we had the normalization factor, which was given by essentially the intensities of the two fields of R1 and R2, which in this case, that was given by E minus of R1 T1 E plus of R1 and T1, then E minus of R2 and T2 E plus of R2 and T2, power of 1/2. If you remember, that was essentially the first order correlation function. After the lecture, we had a little bit of discussion with a couple of you, I think, related to the meaning of the first order correlation function. Today, we will review also those discussions. Okay. So remember, if essentially, if you have two fields, and I have written in this way, I drive this in this form because it's extremely easy to link that to the quantum operators, I mean the mode operators, to annihilation and creation operator. We know very well that E minus, which is related to negative frequencies, that can be replaced by A dagger, and E plus can be replaced by A operator. So I will jump to that later on, but now let's first concentrate on the classical meaning of these. So if you remember, R1 and R2 in our formalism was up beam and down beam, okay? So if you want to find the correlation function between the two fields, R1, T1, and R2 and T2, essentially, you can easily write that way, that this is given by E, E1 and E2, okay, in a short notation, divided, and of course, one of them has a star. And then the other one is given by E1 star, E1, E2 star, E2, power of 1/2. Okay, so that's in a short way that someone can look at the first order correlation function. Good. So we can look at the case that we had previously, which was Mach-Zehnder interferometer. And if I recall well, we had the beam coming in, then we had the pass going up, and we had the pass going down, and then they interfere together, and here we had a detector. And that was essentially what we started with. And we call the red one, we call it E up, and the green one, I call it E down, which the beam is coming from the down. So the interference effect will happen in one given place, right? Which is Z equal to 0. All right. I assume that this is Z equal to 0, that interference appears there. So the field of upside, let's say that passes through the up pass, U up, essentially is given by E power of I, K, well, let's say the vector is along the propagation direction, K L up plus omega T. Okay, and the field that's going from the down is given by E power of I, K L down minus omega T. Okay, so that we assume that the entire the measurement is given in a given time of T, and also the effect only appears when the optical pass has a difference, or the relative phase between the two passes is different. So if you remember in the previous lecture, we had the phase object introduced between the pass of, let's say, 1 and pass of 2. Good, so that is entire the scenario. So this is what we should deal with. And from this, we can calculate what is going on with the G1 function. There are very different ways that people, they do the mathematics. I would prefer to concentrate on the length difference between the pass up and pass down. This is what we are doing essentially. And I assume that both fields, they start from the same time and they arrive at the same time, okay? So I assume somehow this is a monochromatic way. Some people, they say that the starting point is at the given time of T, okay? When they arrive here, one of the field is delayed. So then they look at, if they say that for the up one, it takes the time of T1, for the lower one, it takes the time of T1 plus L D minus LU divided by C. And that's the time difference that appears for the lower beam. Really nothing is changed. I mean, you can do it with the pass difference, or you can do it with the time, the arrival time between the two beams. So if you start with the equation that we had it above, so then the G1 function, which will be given by, I don't keep the functionality. Later on, we will discuss about that. It will be given by E power of I, K with a negative sign, LU minus omega T, and the other one is E power of I, KLD minus omega t. Okay, divided by the average of each power of 1/2. All right, so, and e power of minus I omega t and e power of I omega t, which they have the same frequency, they will cancel out each other. Then what you will deal with is e power of I k, which is omega divided by c times Lu minus, LD minus Lu divided by the denominator power of 1/2. And remember that Lu minus LD divided by C, this is the time difference between the pass of up and pass of down, okay? So if you assume that the two photons, they start from same place, and when they reach to the detector, one of them is going through this pass and the other one goes through the lower pass. Then if the length of this is Lu and the length of this is Ld, then the arrival time will be different for the two beams. This is essentially like that. So as you see that the correlation function, G1, now has only one functionality, which this functionality is the difference between the pass of U and pass of V. So essentially the arrival time between the two paths is different. So that is defining the value of G function. Okay, is that clear? Clear? Okay. All right. So now the question is that how to do the mathematics. It is easy. We can do that also later on. But for this specific case, the average is or ensemble or time, okay? For our case is over the time. And then if you do the normalization, this is essentially is e power of I omega divided by c times tau, okay? Or if you wish, you can write it e power of k dot L u minus L d with the negative sign. And if you look at the interference effect, the interference effect was given by a real part of this function. So a real part of G1 tau defines the interference effect, which is cosine of k L u minus L d. And this is what happens for in Mach-Zehnder interferometer. So essentially, irradiance or intensity, which we did the calculation, E star, now is proportional to 1 plus cosine of k Lu minus Ld. And if someone wants to simplify this, 1 plus cosine, there was a factor of 2 at the front of each, which I took it out. I simplified this. That's the reason that I have written as a proportional to this quantity. Then you will get 2 cosine square of k Lu minus Ld divided by 2, which is a positive quantity, by the way. Don't worry about the being cosine. What does it mean? Look, we don't look at the spatial extension of this. We only look at the case when our detector is a point detector and only measures the intensity. All right. So the detector that we place it here it's not extended in space. is a point detector there. If we want to look at the spatial extension of that, then we have to consider also the spatial profile of our electric field there. Good. So if only, now we can see that if we look at the detector and varying LU with respect to, or LU minus LD, then what you will get as a result of detector power or electric field, or electric current of detector at when the two lengths, they are identical, so LU minus LD is equal to 0, then you will have maximum value. Then when this difference is given by, K times this difference divided by 2 is given by pi divided by 2, then it reduces to 0, then it goes up. So the oscillation that you have is given by cosine square here. So this region is where you have LU minus LD is equal to K divided by 2 is equal to pi divided by 2. So this is essentially 2 pi divided by 2. 2 goes away, pi goes away. Then LU minus LD is equal to lambda divided by 2. So whenever the difference between the paths of the upper and lower beam is given in terms of lambda divided by 2, then you will get no light there. So all light will go to other port, go to the other side of beam splitter. If you remember that there was a beam splitter here, there was one beam splitter here, there was a mirror here, there was a mirror here. Good? Is it clear? So that's a standard procedure of having interferometry. So what is important, in this case, we look at the temporal coherency. When we look at the temporal coherency, we mean that G1 is only function of tau and is not function of R1 and R2. Good? And the correlation function is given by E star of T, E of T plus tau divided by the intensity, which is essentially, if you want to write it in this way, you can write it as E star of T, ET, times E star of T plus tau, ET plus tau, power of 1/2. Here we assume that E1, here we assumed that E1 is equal to E2. So that's the reason that we call it autocorrelation. So that's an autocorrelation of electric field of E. So, and in this case, it will be even much simpler. So you will get E star of T, E of T plus tau. And we know that the average of intensity at different time is intensity by itself. So you may write it as ET star ET. That's all. And in quantum regime, if you remember, that was E minus, and the other one was E plus. That is given by A dagger T, A of T plus 2, divided by average of photon number, which is A dagger T, A of T. Good? Note that bracket notation that we use here, they mean average over ensembles or time. So if you stay stationary, then you will do the average over time. If you have many, many different samples, then you have to do the average over the ensemble. I think we had this sort of discussion previously with Josh. The difference between, Josh, the difference between mixed state and when you get different kind of mixed state, when is statistically mixed or when the state is mixed. Okay, good. So any questions so far? Everything is clear? Good. So hereafter, what I do, I will deal with autocorrelation function. You can do that also for different fields. This is what we have done that. But usually what we assume that the two fields that they are created from the same place. They have the same amplitude. When they have the same amplitude, then easily what you are doing is looking at the autocorrelation between the two fields. So then what I deal with is G1 of 2, which is given by the star of T, E of T plus 2, divided by the intensity, which is E star of T, E of T. Good. And also, of course, I know that in the quantum regime, that will be given by annihilation creation operator. All right. What I can do. Let's do a little bit of mathematics. So also, I note that people also sometimes they use G1 of 2, which is not a normalized G function. This is defined as E star T, E of T plus 2. These non-normalized or normalized G function or first order of G function. Good. Before doing and performing some calculation for different statistic and getting the result of these, let's have a little bit of mathematics and understand the meaning of G1 function. Good. In order to understand the meaning of G1 function, let's do the Fourier transform. So the ensemble of E star T E T plus 2 is equal. This is, I assume that the field is stationary, so I'm not dealing with ensembles. When I'm dealing with ensembles, then I can do the same scenario, but let's, for the time being, we assume that this average means the average over the time, okay? So this means that is integral from minus infinity to plus infinity of dt E star of t, E of t plus 2. Good? This is what I have as the time average. I take the field, I just displace it by the time of 2. Then what I do, I will multiply and I look at the value of this. I do the Riemann integral. Good. That can be, in laboratory, that can be done with a summation, simply. Do the summation for infinitely small time interval. Good. I know also from optics, Fourier optics, that E is, at the time of t, is linked to its Fourier transform by E omega e power of minus I omega t. Do you agree? Which I'm doing the frequency integral from minus infinity to plus infinity. So, for example, if I have a pulse of beam, this pulse of beam is expanded in terms of different component of the frequencies. It looks like I have many different frequencies, and what I do, I will look at a specific wave function in the frequency domain, and I create them. This is the technique that people in high harmonics, or let's say ultra fast optics, they use to shape a pulse. So you want to create a pulse which has this pattern in time. What you do, you go to Fourier plane, to the spectrum plane. So you go to frequency, and then you manipulate the E omega, and then you come back to the position representation. And from there, what you will get these pulse. How people, they go from position to Fourier to frequency domain by a grating. So you place a grating, the different component of frequency, they will be distributed in spatial. Then each of them, you manipulate them, and then you combine them coherently. And then you go to the position representation. These people, what they do. So, but what is important, that any pulses that you do have can be expanded in terms of Fourier transform. Lovely. So ET is given by 1 divided by square root of 2 pi, integral of minus infinity to plus infinity d omega, E tilde of omega, e power of I omega t with a negative sign. And the same scenario happens for this one. But remember, I have to be careful that I'm not using the notation of omega. I use the omega prime because it's a different integral. So it should be integral of minus infinity to plus infinity, 1 divided by square root of 2 pi, of course, the omega prime. Then I have E tilde of omega prime. Is the same function essentially because it's the same field. The only difference is that now is omega prime. And then you have e power of minus I omega t plus 2 prime, of course. Good, let's do that. So let's do the mathematics. I get integral of dt, integral of d omega, integral of d omega prime. And I do have 1 divided by square root of 2 pi, 1 divided by 2 pi, integral of this. Then what else I have? I have E star, that one should be star, of omega, e power of minus plus I omega t e power of minus I omega prime t. And then also I have e power of minus I omega tau. Sorry, let's keep it inside because the integral is still there. E power of minus I omega prime tau. And then I have e of omega prime. So let's cast them in the proper way. I will write that as 1 divided by 2 pi integral of d omega integral of d omega prime e star of omega e of omega prime. Then what else? I have e power of minus I omega prime 2. And then I have integral of dt e power of I omega minus omega prime t. I think that's all. Good. What's this integral?
Delta omega minus omega prime and 0.
Omega minus omega prime. Okay.
Yeah.
That's all?
With a coefficient of 2 pi?
Exactly, with the coefficient of 2 pi. Then what I get integral of d omega. Delta of omega minus omega prime everywhere is 0. Only when omega is equal to omega prime, that value, only that cases will remain. So all omega prime will be replaced by omega. Then I will get d omega e star of omega, e of omega, e power of minus I omega 2. Good. So e omega tilde is the Fourier transform of the field. E omega times E star omega. This gives you what we call it power spectrum. This is what you can measure with a spectrometer, essentially. And then that results in d omega, S of omega, e power of minus I omega 2. Remember, S omega is power spectrum and is given by E omega power of 2. What is this quantity that I did the calculation for? Is G1 of 2. If you assume that the field is normalized, already the intensity is normalized to 1. So if you assume that usually what we do is we normalize the intensity as well, then for a normalized field, G1 of 2 is essentially integral of d omega S omega e power of minus I omega 2. What does it mean, guys?
They're a Fourier pair.
Pardon?
They're a Fourier pair between the two.
Exactly. So the power spectrum is the Fourier transform of the correlation function, first order correlation function. And of course, as you say, they are pairs. Okay, or they are conjugate, if you want to call them in mathematical formalism. All right, so the first order correlation function will tell us what's going on with the spectrum, power spectrum of the beam. How good the beam is monochromatic. Okay, so for example, if S omega is delta function, right? Then G is equal to 1. This is what we see, absolute value, of course. I mean, that will be sinusoidal, but the absolute value will be equal to 1. And that's the meaning of being a good coherent beam. This is what you get it out of a laser beam. So last time I made a joke with the people that they were staying until the end. I say that this is a famous question that people usually they ask you. I mean, they say that what is the size of photon, right? You may receive this question. Some people they say that is the wavelength, right? People they say that is wavelength of light. The proper answer is the coherent length and coherent size of the beam. So if you create a photon with the special coherency of LC, right, which means that the initial and the end of this, they preserve the same phase information, then the end and initial one, they will interfere with itself if you put them in an interferometer. So if you put a photon to interfere with itself, like a Mach-Zehnder interferometer that we have done, even these long distances, let's say for a Heine laser, we can do the calculation. It will be almost about a few kilometers. So your Mach-Zehnder interferometer can have a different length of kilometers, okay? Still, you will get interference. And you can attenuate the Heine laser to go to the, let's say, 1 photon per time, or the Poissonian distribution in such a way that probability of getting 1 photon is high. I mean, that was one of the questions that you had in your exam. Even in that regime, that single photon interferes with itself. While if you do it with the thermal light, that they don't do that. They don't go with a difference of, let's say, 100 kilometers. Why? Because they don't have a special coherency. They don't have a longitudinal coherency, enough longitudinal coherency. And that is the size that you can see the wave packet there. Okay. So it is important to note that the power spectrum is the Fourier transform of G1. Now I can multiply both sides by e power of I omega prime t, and then doing the integral and inverse the Fourier transform. Then what I will get that S omega is equal to 1 divided by 2 pi integral of d2 g1 of 2 e power of I omega 2. Do you know how did I get that? I multiply both sides by e power of I omega prime 2, and I did the integral on d2. If you do that, then you will get, you will inverse the Fourier transform, and you will get a power spectrum in terms of the coherent length. This is a very useful technique, by the way. It's classical, purely classical, but people, they use it in the laboratory. Now, let's do a little bit of mathematics. But before doing so, let's look at the property of G1 function. G12 was given by E t star E t plus 2. Can someone tell me what is G1 minus 2? Of course, there is a normalization factor. The change of tau to minus tau will not affect the normalization. That's the reason that I didn't care. You can do a little bit of mathematics by yourself, and I'm sure that you will get it quickly.
Would it be the complex conjugate
Of
the whole thing of G1 tau?
G1 of tau or minus tau?
I think G1 of minus tau is the complex conjugate of G1 of tau.
Exactly. Okay, that's a property. Easily can be proven. Look at this expression, guys. Look at this one. I will change tau to be minus tau. Do the change of variable, and I'm sure that you will get that quickly. Okay. Good. So I need that property for the following expression. So S of omega, a power spectrum is 1 divided by 2 pi, integral of d tau, G1 of tau, e power of I omega tau. Lovely. Then, that integral is going from minus infinity to plus infinity. So it means that you have 1 divided by 2 pi, integral of minus infinity to 0 plus integral of 0 to infinity of d tau e power, g of 1 of tau e power of I omega tau. And then breaking the integrals into two integrals, then you will get integral of minus infinity to 0 of d tau G1 of tau e power of I omega tau plus integral of 0 to infinity of d tau G1 of tau e power of I omega t. So here, what I do, I will change tau to minus tau. Then d tau will be minus d tau. The interval will be plus 0 to plus infinity to 0. That becomes G1 minus tau, and that becomes minus I omega tau. Good. Just we discussed that. That can be replaced by G1 of tau star, or in general, the entire of these things is G1 of tau e power of I omega tau star. And minus d tau will change the interval from 0 to plus infinity. Then what you will get 1 divided by 2 pi integral of 0 to plus infinity d tau of G1 of tau e power of I omega tau, that is star, plus integral of 0 to infinity d tau G1 of tau e power of I omega tau. And that is z plus z star, which is 2 real part of z, to simplifies with 1 divided by 2 pi, and that is the real part of integral of 0 to infinity of d tau G1 of tau excuse me, e power of I omega 2. And that is a theorem, which usually I forget the name, is Werner, oh gosh, I have not written down. Yeah, is Wiener Kin Chin theorem. You will see that that will be extremely useful. Okay. So now I know how to calculate G1 function, and I know what is the meaning of G1 function that is related to the power spectrum. And even I can calculate power spectrum based on a G1 function, because they are Fourier conjugate of each other. Online teaching is just awful. You have to pay attention to almost everything. Your computer is not out of battery. Your iPad is not out of battery. Your pen is not out of battery. You have to allow students to come in. You have to see all of the students, and yeah, oh my God. Anyway, it will be over soon. So, and you will see in a few minutes that that is really, really useful. Let's calculate the G1 function, and then of course the power spectrum for different cases. And those different cases will be, the first one is thermal source, right? Which has a certain property, and we will discuss about the property of that. So usually, how do you get a thermal source? Let's say, assuming that you have a gas of atom, and these gas of atom, they are excited, and then they will decay. And we know very well that when you excite a gas, and essentially you keep them in a certain temperature, which is what you know from Maxwell-Boltzmann distribution, then they have a certain velocity. So all of those gases or atoms, they are moving around, and then sometimes they hit each other, right? Or they hit the boundaries. And anytime they hit the boundaries, there will be a change in phase. And prior to this one, what you will get the quantum mechanical picture, which is getting a certain frequency, a sharp frequency that the field that is emitted. So now what I assume that I have ensemble, in this case, I have ensemble of gases, or a gas, which atoms randomly move around. And what you get as a consequence, you get collisions between them. So this, if you look at the field in time, you will get oscillation from those fields, from atoms. But suddenly, there is a collision that happens. And what happens, for example, let's ask someone who, Manuel, can you say to me that, for example, this is an atom which is radiating a photon or electric field, but suddenly is having a collision with another atom. So then what is happening? The frequency will not change, right? The only things that will change is the starting point, right? So it may start from, let's say, here again, like that. And again, another collision will happen in another place. Then you will get, let's say, a starting point here. This is the source of random phases. So if the phase is constant, let's say 2 pi, and here is pi divided by 2, here, for example, is 0, or is another quantity. So the consequence of collisions between atoms will just change the phase of electric field in completely random fashion. And that happens very quickly, by the way. And if that's the time, this is associated to the regions, the jumps that we have seen it. And that is the phase. So phase is function of time, essentially, of the electric field. And what happens? We have too many of those atoms. It's not only one single atom that does this job, but we have, let's say, a million of those atoms, which they move around, and although you keep them in a certain temperature and you expect to get a monochromatic wave from them, or partially monochromatic wave from them, you will get different phases from those radiations. I saw a very nice movie once that they say, of course, if you look at that region, or this region, or this region, even thermal source is coherent. Okay? But the point is that this oscillation is so quick, which essentially what we see is the entire of the effect, is the entire of those phase jumps that happens around. All right, so let's do the simulation. So we have n number of atoms. The electric field that I'm dealing with, the electric field of total, which I'm dealing with at the time of t, let's see, what is the notation that I have used? Yes, at the time of t, is given by summation of all of those electric fields, which they are oscillating with the frequency of minus I omega t, but different phases, I, phi, I, which this phase is time dependent. I is changing from 1 to n. And of course, I assume that all of them, they have the same amplitude of A0. Anyone having question? Tenglu, clear? You're the only one taking your heads and say, oh my God, what's this guy saying? Good. Fantastic. So just to review, so the emission from one single atom is e power of I omega t plus I phase of time, which is this phase that is changing here, which is time dependent. The frequency of emitted photons for all of the atoms, they are identical. So omega is the same for all of them, almost. And then what you will get, you only get the phase, which is different for different atoms. That's the reason that here, the summation only affects on I, on phi, right? Good. So I know the ET, which is quantity. The amplitude is the same for all of them. For simplicity, I from 1 to n atoms, e power of minus I omega t plus I phi I t. How can I calculate G1 functions? Oh, let's say, yeah, G1 function. I have to do the average of ET star, right? of E t plus 2 on ensembles. Remember, these are the ensembles and time. Okay. So then what I deal with is E0 absolute value, because it's the field multiplied by itself. Then I have two summations, summation over I, one from 1 to n, the summation over j, which is 1 to n. Then I do have e power of I omega t plus, with the negative sign, sorry, this one is with plus. The other term is with negative I phi I of time multiplied by e power of minus I omega t plus 2 minus plus I phi j t plus 2. And so average. Okay, that can be simplified as E0 power of 2, e power of minus I omega 2, summation over I 1 to n, summation over j 1 to n, e power of I phi j t plus 2 minus phi I of 2, sorry, t. These two terms, they are constant, independent of ensembles. They will be out of the ensembles. You will get E0 power of 2, e power of minus I omega 2. Then you have to do the ensembles on I equal to 1, or let's say I and j from 1 to n, e power of I phi j t plus 2 minus phi I t average. Good. So can someone, let me ask someone, Henry. So since you volunteered to answer to one of those questions, let me ask you one. So this is the average, right? Which is, excuse me. This is average, so it means that, excuse me. We do it on different ensembles, also on different time, right? Time is changing from minus infinity to plus infinity. Can you tell me what happens when I is not equal to j? So for example, you have for 1 and 2. So it will be phase of 1 at the time of t plus 2 minus phase of 2. When I is not equal to j. Then we have this term, which is exponential of I phi I plus t plus 2 minus phi I. Is there any relation between these two?
No.
They are completely random.
Yeah.
They are completely random because they are coming from two different atoms. So averaging over them will be 0, no doubt. So essentially, the entire dose summation will be simplified only to one summation, which is when we have I equal to j. The rest will be 0. Even I equal to j, they are identical copies. So they are random atoms, but the behavior they have, individually, they look like each other. So that can be replaced by E0 power of 2, e power of minus I omega 2, n of those average, which is e power of I phi j of t plus 2 minus phi I, sorry, phi I t plus 2 phi I of t. Do you agree? So I jump a step. The step is that will be simplified to summation of I from 1 to n of e power of I phi I t plus 2 minus phi I of t. And then I say that the average of a summation will be summation of average. So I swap this, I took the summation out of this, and I say that those look like identical copies, which they have random behavior. So what I have done, I say that this is equal to n of those quantities. If it needs further clarification, just let me know. I will explain further. Anyone? Is it clear? Good, Karsh? Good. Okay.
So those are both phi I now, not I and j.
But all of them, they are I. Yep. I have not written j. So this is I, perfect. This is I, and then you will get n. Why I get n? Because I say that the average of this is equal to summation of I from 1 to n of this average, right? And then I say that I'm taking average of a quantity n times, then that's the result, okay? So here also is I. Good? Lovely. I think now we are close to get the results. Let's see how can we simplify this. Anyone can make a guess how we should calculate these. Remember, this phase jump that appears is due to what?
To the collisions.
Exactly. What does it mean? Manuel, can you show it with your hands to me?
I mean, I don't know what to show. That's the
problem. So this is an atom which emits photon, right?
Mm-hmm.
Then these atoms is coming and hits another atom. Then the phase is jumped to another quantity, right? So this phase jump or this quantity that we do have is related
to the photon they emit.
Exactly, related to the collusion and the photons that they emit. So if there is no collusion, that quantity will be 1, right? But there is a collusion, and the probability of collusion happens based on the thermodynamics nature of that. And we know that there is a flight time for atoms. If it looks like that you have a ping pong ball and you throw it among many different ping pong balls, and what is the probability that you will get that? So if the time will increase, definitely you will get you will hit another ball. But if the time is short, then you may not see that. So you can assign a time which this time is the time of flight, which one atom is hitting another atom. And that time is given exponentially. So the entire of this is related to the flight time of atom, which in principle is given by a probability distribution, which this probability distribution, I will write it down here. So the P tau D tau, which is the probability of heating another atom, is given by 1 divided by tau 0 e power of minus t divided by tau 0 d tau. Okay, this is what you will get for the collisions. And tau 0 is the flight time. Good. So if you do a little bit of mathematics, then let me see if I have not missed any of those expressions. Flight time. Yeah, so then that is given by E0 power of 2, e power of minus I omega tau, n number of atoms, of course. And then this is a probability that you will heat the atoms. So it starts from tau to infinity. And that is given by pt dt, which in total integral of e power of minus t divided by tau 0, that can be simplified also. I mean, you can do the integral, it's not a big deal. You will get E0 power of 2, e power of minus I omega tau, n, then e power of minus tau divided by tau 0. So on the side, I will write the integral, by the way, integral of minus tau to infinity of 1 divided by tau 0, e power of minus tau divided by tau, let's say, sorry, minus t divided by tau 0 dt. Then that is 1 divided by tau 0. Integral of exponential is exponential, that will be minus tau 0 e power of minus t divided by tau 0 from tau to infinity. That is given by tau 0 e power of minus tau divided by tau 0. It goes away with this, and then you will get that result. Good. So G1 function, after the normalization, that was a G capital, guys. After the normalization, then you will get e power of minus I omega tau, e power of minus t divided by tau 0. I should have written that the frequency of oscillation at the beginning, from the beginning here, I should have said that the frequency of oscillation is omega 0, just to clarify that we are dealing with a single frequency of omega 0. Here is omega 0, here is omega 0. Here is omega 0, then here is omega 0, omega 0, omega 0. Okay. So what is the G function? What is the form of G function?
It's a damped oscillator.
Is decaying.
Yeah.
Right? So if I have to look at the real part of this or imaginary part of this, because it's exponential of I omega 0. So what you will get, indeed, if that is tau, and that is the quantity, then it starts from 1, right? It decays. if I look at the real part of this, real part of G1 of tau, people, they look at the absolute value of G. They don't look at the G1, the quantity of this. So it starts from real part is a cosine, it starts from maximum. Okay. It's like that. Okay. And the frequency is omega naught. As I say, in many books, they don't look at the quantity of, let's say, real part of G1, they look at the absolute value of G1. If you look at the absolute value of G1 of tau, the absolute value is look like this. So this is absolute value of G1. It starts from 1, note that, and then it decays. Okay, so let me ask someone. And this decay is given, let's say, with the length, which is given by tau 0, right? Which is 1 divided by E of 1. Okay. Let me ask someone which might be experimentalist. Cicera. What does it mean, Cicera?
Like how it decays on both sides?
Yeah, but what is the meaning of G1? What is the meaning of this plot?
So like it will decay before the next collision happens?
Yes, but it has a specific meaning. Look at the G1 in terms of interferometer.
Okay.
If you remember, G1 was look like an interferometer, looking at the interferometer. The visibility of interferometer, or let's say the visibility of interference, will be less and less when the time difference between the two paths is longer than tau 0. Okay, this is what we get. So who else? I mean, anyone has insights that want to share with us about this, guys? Excellent, Cicera, thank you. So can you make an interference with halogen lamp? Thomas is moving his head, so as a sign of yes. Okay. So Manuel, can I make an interference with a halogen lamp?
I think yes.
Okay, Josh.
I'm going to say it's going to have a very small coherence length, so it would be difficult.
What do you mean by small coherence length?
Or sorry, you would need to make sure that your interferometer is small enough, right?
We just discussed that, right? In terms of G1, can you tell me what you mean by that? I mean, that's exactly the point, right?
Right.
The tau 0 is extremely small, right?
Right, yeah.
Okay, this is what we mean. So you will get fringes, but it's extremely, it's a really short difference between the two paths, right? Anyone agrees on this? When I was a master student, I bet with one of my my friends, a PhD student there, and I made an interferometer with a halogen lamp. It essentially looked like a candle. but it took me 2 weeks to do that. And as a hint, for this sort of interferometer, you cannot do it with Mach-Zehnder, because Mach-Zehnder requires you that the two arms really to be very close to each other. Either you have to do it with the Sinach interferometer, right? Because you know the Sinach interferometer, the beams goes one counterclockwise, the other one goes clockwise, but in the same loop. So anything that happens, any vibration will happen in both sides, okay? You can make a little bit of delay between the two by just controlling the mirrors. Or you can do it with Michelson interferometer. Michelson interferometer will allow you the two beams will be orthogonal to each other, moving them, one with respect to the other one. So Mach-Zehnder is not a proper way to do this sort of experiment. But very good point, guys. I mean, good catch. Excellent. Haha. Now, as an exercise, guys, I know G1. Can I calculate SW, the power spectrum of these? Yes. So SW is 1 divided by pi. Now you do appreciate why I spent time on deriving that equation for you. Is a real part of integral of 0 to infinity of G1 of tau Fourier transform. I think it was 1i omega tau d tau. Good. Anyone can make a guess.
It's a Lorentz function.
Exactly. Decay will give you Lorentz function. Excellent, excellent, Josh. So it is. I don't keep the coefficients, guys. So it is proportional to 1 divided by tau. I think it should be 1 divided by 1 divided by tau power of 2 plus omega minus omega naught power of 2. So if you go to frequency domain, what you will get, this is not G function, remember? This is SW. Then you do have a peak around omega naught, but then it decays. It decays. Oh. Sorry. Okay. Is a Lorentz function. So the power spectrum, if you look at the spectrum of this beam, it has a Lorentz form. Good. This is one thermal light. This is what you get it from mercury lamp, helium lamp, argon lamp, and etc. So this is exactly the theory that you will get. They have a spatial coherence, a temporal coherency and spatial coherency, but it's extremely small. Okay, good. And you can look at what is the temporal coherency by just only looking at the power spectrum. You can put a spectrometer and you can measure these, and then you have an idea about the G1 function. Good. Let's solve another example. Second example. Doppler broadening. What is happening now? The frequency also is not the same. Phase is the same, but the frequency is not the same. Why? Because atoms, they have different velocities. When atoms, they have different velocities, then you expect the spectrum will change. Good? So electric field, now ET is given by E0, summation of I from 1 to n now is e power of I with the negative side omega I t plus I phi I. Now phase is not function of time, but frequency is changing. So Felix, can you tell me what is et plus tau now for this function? Is E0?
So the E0 sum I to n.
Right.
E negative I omega times t plus tau.
Exactly, which is minus I omega I tau, right?
Yeah. And then phi I at t plus tau.
But the phi is constant. That was the hint. Phi is constant anymore. So the only function, the only function is this.
Yeah.
For the sample, which is changing. Good. So let's calculate G1 of tau, and then we will normalize it later on. G of tau is given by essentially E star of t, E of t plus tau, which is integral of, let's do not integral first. Let's go to the last stage. That will be integral, the average of E0 power of 2. Then you do have two summations, I equal to 1 to n, j equal to 1 to n, because they are two different fields. The first one goes with a star, which is -1, that will be positive, e power of I omega I t plus, minus I phi I. Then we do have e power of minus I omega I t minus I omega I 2 plus I phi that's all of them, they are j. Good. And that's average. Good. All right, so let's do the mathematics. E0 will be out. Then what I have is the average of, average of I and j from 1 to n. Then I multiply both terms together, e power of I omega t will remain. So it will be e power of I omega I minus omega j t plus I phi j minus phi I. Then what I have, what else? I have plus, minus I omega j tau. Okay. So the phases that we do have, these phases, they are completely random, right? They're from I and j. So then we expect that no contribution will happen because they're completely independent. They are completely independent. Then we do have E0 power of 2 summation of I j equal to 1 to n. Then I do have the summation e power of I omega I minus omega j times t minus I omega j 2. All right. So can someone tell me what I expect for this scenario? I'm taking the ensemble and the time average as well. So let me ask Eric. What do you expect for this, Eric?
I expect the sort of terms where I and J are different to vanish because you're taking a time average of the oscillating exponential.
Exactly. So if you are taking the time average of oscillating function, when these terms, they are not identical, that will be vanishing. When they are identical, that will be equal to 1. So this is what we expect. So essentially, then I will get E0 power of 2 in the similar fashion, and then I will get the average of E power of minus I omega. Let's do that. Let's write it this way. I from 1 to n omega I of 2 this way. You agree? Anyone? Clear? Good. So the tricky part appears here. And of course, that is no need to say that is E0 because we assume that they are independent atoms, that they are moving around. Then that will be look like n e power of minus I omega I, let's say omega, one single frequency that we assume 2. So what I have done, I assume that I have n different ensembles, which a frequency of omega naught is the essential frequency of them. Good. For Doppler broadening, this is this expression can be expressed in terms of Gaussian function. So essentially, the entire of that will be given by E0 power of 2 and 1 divided by square root of 2 pi of delta integral of d omega e power of minus I omega 0 2. That's it. Sorry. Omega 2. And then e power of minus omega 0 power of 2 divided by 2 delta power of 2. This is essentially what we consider for Doppler broadening. Oh, very nice music, Felix. I muted you. Cool.
The album comes out soon.
Pardon? No, album, I don't buy it. I will come to your concert. Good, good. Fantastic. Sorry, it will be quick. Now we are done, and then we can have a break. So that will be E0 power of 2 and 1 divided by square root of 2 pi delta. Then we have to do the integration of this, which is essentially a Fourier transform of a Gaussian profile. And what you expect from a Fourier transform of a Gaussian profile, you will get the same result. So I have already done that. That will be e power of minus I omega 0 2. And then we get e power of minus 1 divided by 2 square delta square. Okay. So G1 of tau, which is a normalized one, is proportional to e power of minus I omega 0 tau, e power of minus 1/2 of tau square delta square. So what does it mean? That for Doppler broadening, if that is tau, then again, G function will start from -1 to 1, okay? But the the envelope is not anymore Lorentzian function, but is a Gaussian profile. Okay. Of course, symmetric, remember. Okay. And then that is between, that's a function of G1 of tau, real part of this. The real part is changing from this quantity. The oscillation, let's go with real, it's a cosine function. Then it's so from 0, it goes like this. Okay. And here, when tau is equal to 1 divided by delta, then that 1 divided by square root of 2 delta, that gives 1 divided by E. Let's do that. Here will be 1 divided by E. Tau is square root of 2 of delta. Okay. And in some other books, you may see it like people, they look at only the absolute value of G1 of tau, and no surprise that the absolute value of G1 tau will be a Gaussian. Okay. How many people they have seen this before? No one. Okay. This is one of the reasons that people, they show photons like this. Right? If someone is drawing photon on a board, they draw it like that. Because it's the standard nature that we assume that we have a Doppler broadening, and we have the wave packet is located in specific dimension, okay? And that is dictated by the coherency that we know very well. And now, again, you can use the theorem and calculate what is SW. I think I have done that SW as well. SW is given by, gosh, let me see. SW is given by 1. You can do it at home. It's not really difficult task. 1 divided by pi. Oh, let's do that. Simplify even. I have not simplified this. 1 divided by square root of 2 pi delta e power of minus omega 0 power of 2 divided by 2 delta square. It is exactly what I consider as a spectrum for the beam. So and then that is the spectrum that we expected. And so here it will be Gaussian profile. Okay, around W naught. Okay, so I will stop here. It's 45 minutes almost that we started. Go and have some rest, and then we will see each other in about 15 minutes. Okay, and we will review this with because we have not done the calculation for coherent light. We will do that for coherent light, and we summarize what is happening for thermal light and for coherent light and Doppler broadening. Okay. now we do have a clear picture about G1 function. Let's review it again together. So we look at two different cases. One was for stochastic light, essentially, which collisions happen, or thermal light, that collisions happen. The other one was Doppler broadening. Let's calculate also the another case, so which is coherent light. What is a coherent light? What do you expect?
There'll be some correlation in the phi terms.
Correlation is in the phi term, or phi is constant.
Like in that phase. Sorry.
Phase is constant, right?
Yes.
Because the field that you do have is ET, which is ET is given by exponential of I omega t plus a phase, which is constant, right? If you do G1 of 2, which is essentially, if you look at the ET star and ET plus 2, you will get e power of minus I omega 2. That's all. Because the phase is constant, and then when you look at the conjugate of that, they will cancel out each other. This is the definition of monochromatic wave. So, and then for the first one, what we got G1, which is proportional to e power of minus I omega 0 t, sorry, and then e power of minus t divided by 2, right? 2 divided by 2, 0, sorry. For the Doppler shifting, Doppler broadening, we got e power of minus I omega 0 2. I don't remember what was the result we have written here. Okay, yes, thank you. E power of minus 1/2 of 2 0 delta power of 2. Okay, so we do have it for coherent light, we do have it for thermal light, and we do have it for Doppler broadening for all of these three cases. Now, what we look at it, we look at the absolute value of G1 of 2. True? So first of all, what do you expect for G1 0? Anyone that can get the result, I will get 1 mark. What is the value of G1 0?
A delta function?
No.
Ah, shit.
For
One?
any light. Who? Henry?
1?
Exactly, Henry. Bravo. You will get 1. Why? Because it is E star at time of t, E of t plus 0 divided by E star t, E t, which is 1, no doubt, okay? You can even see it in the quantum language. The quantum language was a dagger at t, A at t plus 2 divided by photon number average, which is A dagger, which again is 1 for if 2 is equal to 0. For 2 equal to 0, that is 0. That is 1, sorry. All right. So for all of them, it starts from 1. That's the point. Okay. So I look at 2 and I plot absolute value of G1 of 2. For any of those cases, it starts from 1. For coherent light, what it will be the result? Josh? Oh, Henry, go ahead. I think
Always 1?
always 1. Thank you. This is the coherent light. Coherent light. Josh, can you tell me for the rest? Please. For thermal, for example, thermal light.
Right, you're asking
collusion.
for G at 0, right?
It starts from 1, right, for all of them.
Yeah.
And then it drops exponentially, right?
Yep.
And this is for collisions. And for the other case, Doppler broadening, it goes like Gaussian. True?
Wouldn't the Gaussian, no, sorry. But actually, wouldn't the Gaussian decrease faster than the Doppler?
That's all depends on the delta.
Okay, fair.
It
Yeah,
can be
close.
faster, it can be slower. So in this specific case, I show narrow because usually what we expect that the coherence length due to the Doppler broadening is a little bit longer than the thermal one.
Okay.
But that's a valid question. That all depends on the value of delta and tau naught. So here, remember, that is tau naught. Okay, which the value of G1 decreases to 1 divided by E. And then for Gaussian, that is what we show, it is from here to here, square root of 2 of delta. Okay. Clear? Beautiful. Good. So that's a reason that monochromatic light, the coherent length is infinity, right? While if you have a Doppler broadening, which is what you get it usually in the gas, then you have a certain value for the coherent length, and then for thermal light, that's the case even faster. Okay. So those are important factors. Now, I can go even, I can define the other scenarios, but let's look at a specific example of this, which is important. I mean, in the same fashion, I can define what is going on with G2 function. But let's go historical on the G2 function. So let me do a little bit of mathematics for the case when people, they use interferometer to determine the size of stars, okay? Look at the dimension of the stars. So what they had, at that time, they had interferometers, and the interferometer was like this. So they had a telescope, a single telescope, by the way, remember that? They had a single telescope, and they got light from 2 parts, and they interfere together. If I want to be careful what I want to say as a single telescope, I mean these two can be 2 telescopes essentially, but the light that is coming in, they will interfere in a single plane. Okay, so those are mirrors. You can have two telescopes watching the, let's say, different part of the sky, and then the light that you collimate them, get them together and interfere them together in the same plane. And what you can vary is the distance between these two, which I call them R0. Okay, how far are the two sides that they capture the lights? So if you have a star, essentially the star, gosh, how should I show a star? Okay. Oh, yeah, okay. I will go with sun. It's not sunflower, it's sun. Then light can come from one side of the star or it can come from the other side of the star. Right? So because it is not a point object, it has a dimension. True? When it has a dimension, then this is what I expect. And the point is that to find out phi. What is the spatial extent of the star? Is the question clear, guys? So let me say in a lay language, an easier way. I was working in an observatory back when I was a bachelor student. And we were aligning the telescope, and it is interesting. It goes back to 1997, almost 23 years ago, almost 24 years ago. At that time, we had even the CCD camera cooled down to minus 30 degrees just to reduce the noises and blah, blah. One night we were, I don't know, by accident, when we control the motor, we bring it down, we were able to watch one of the boards in the city, which was about 20 kilometers, not 20 kilometers, maybe about 8 kilometers far away. And we were able to see that board there. Now, assuming that when you are watching a board, the light can come from different side of it. So, for example, if this is the bottle of water that I have, so you can watch, the light can come from this side, which is the end of the bottle, or it's coming from the top of the bottle, okay? And the point is that this light is totally incoherent, right? Because this part and this part, they have no phase relation between them. Atoms are excited here. If that's a star, atoms are excited here, then you will get emitted light from the two sides, which they have no relation between them. And the point is that to determine the size or the angle of the star. So then the light is that is coming to the telescope one from this side essentially has a k vector of k. From the other side has a k vector of k prime. One of them is k, one of them is k prime. Let's go with this way. Okay, the same scenario. That is k, and the other one is k prime. Good. But one is collected by telescope 1 and the other one is collected by telescope number 2, and then they will interfere together. So this one, I call it number 1. Oh, let's go with different color. And this one, I call it number 2. Good? Lovely. So what is the field at telescope number 1? Field at the telescope number 1. is the field that is coming from the star. Okay, I will call it K. Then e power of I, K. Look, one is coming from this side, which is K. And the other one is coming from this side, which is K prime. All right. So EK dot R, 1. Oh, let's write it as a K. And then I will write it in a different way. EK prime, e power of I, K prime dot R. So this is the field that you will get it at each telescope. For telescope number 1, what you'll get 1. For telescope number 2, you will get 2. Okay, so either you will get 1 or 2. The total field at the screen is no tilde, because I assume that there is a polarizer at the front of it. I didn't put exponential of I omega t because I assume that there is a interference filter there which takes away all frequency and only allows us to have one certain frequency. We know that all of those preconditions that we have to apply to get the interference. Okay, so the total field is given by electric in the E field at 1 plus E field at 2, which essentially that will be E K e power of I K dot R1 plus E field of K prime e power of I K prime dot R1 plus E K e power of I K dot R2 plus E K prime e power of I K dot R2. K prime, sorry. Good. So 2 of them, they have K prime, and the other 2, they have K. One of them has R1, the other one has R2. And that's a contribution that you will get it at the screen, okay? And this is the field here at the screen. Good. Our detector will not see the field. It will see irradiance with a coefficient which is quantum efficiency that we know, or efficiency of detecting the photons. So essentially, EI is given by K, which is the quantum efficiency, or let's say call it eta. I think previously we used eta. ET star times ET. And we know very well that also our detector doesn't have a time resolve. So essentially it does the average on frequency and time. So then you have to do the average on time. Clear? I think we discussed about that, that the frequency that we are expecting is 10 power of 15, then our detectors, they have a nanosecond resolution. So, or even if it's so fast, it's picosecond resolution. So essentially we cannot resolve that. Then we get eta, and then we have to multiply them together. So we will get EK e power of I, gosh, I have to repeat all of them. R1 with a negative sign, and that is star, plus EK prime star e power of I K prime dot R1 plus EK star e power of minus IK dot R2 plus EK prime e power of I minus IK prime dot R2 times the field that you have it here, time average. Good. How many terms do we have?
16.
16 terms. So we do have 16 terms. I could have been much clever. And what I could do is just gathering the EK together and these two terms together. Okay? So I do have 16 terms. But I know that the light that is coming from K and the light that is coming from K prime, they're completely independent source. True? So the time average on the two will be 0. Do you know what I mean? I want to see your face just to have a feeling about your reaction. So whenever I deal with this, which is EK prime, okay? Or star or whatever of these, what I expect. Since K and K prime, they are independent, I'm expecting that it will be on the time average will be 0. Clear? Manuel? Good. So if we do the mathematics, which we can do that, and essentially what we will get eta. From this term, this term, this term, and this term, we will get 4 identical terms, which essentially they are look like EK square plus EK prime square modulus with a coefficient of 2, because one we have from the first term contribution, the other one from the third one, and then second and fourth term contribution. And then what else I do have? Plus eta, then I get eta, oh, let's say EK square modulus e power of I K dot R1 minus R2 plus complex conjugate of this, plus another term, which is EK prime power of 2 e power of I K prime dot R1 minus R2 plus complex conjugate. Okay. Clear, guys? This is what we expect as an intensity to see. Four terms remain, which I have written here. They are essentially 4 terms. Then I have 2 terms here. I have another 2 terms here. So essentially 8 terms will remain, and the other 8 terms, due to the facts that this is valid, I will get 0. Do that at home. It's not that difficult. It will take 5 minutes to expand that. Good. So the brightness from the 2 parts, assuming that the 2 parts of telescope, they will capture the same intensity, or let's say the 2 sides of the star, they have the same intensity. Then I can factor these out. And essentially what I will get intensity, which I assume that these 2, they're identical, then the time average of them will be identical. Then what I will get, even I can factor it out, is up to you. So assuming that EK power of 2 is equal to EK prime power of 2 is equal to I0 intensity, which is 0. And then that will be equal to 4 eta I0. Then I will get 1 plus, from the first one, I get cosine of k dot R1 minus R2. From the second one, I will get cosine of k prime dot R1 minus R2. Okay, this is essentially what we will get. There is a factor of 2 which I have taken out and I put it in the 4 pi. Clear, Manuel? It's good. The way camera is on, I can see who is laughing, who is smiling. It's very good. Yeah.
I'm working. I'm paying attention to you, and I have all open.
I know.
And sometimes I get funny messages, from
I
people
know.
also in the group.
Exactly. I know. I know that the online system allows you to do multitask. Being multitask, and sometimes people they're sending you, look at the ties of Ibrahim. He's not online. Some funny things. Good. So now I think it's clear that is cosine with a factor of 2. That is also cosine with a factor of 2. One of them has a k, the other one has a k prime. All right. Now, if we do a little bit of mathematics, so when you deal with two cosine terms, which they are not identical, always we can simplify them in terms of product of two cosine. This helps you to understand which term provides fast oscillation, which terms provides you less oscillation, okay? Or lower frequency oscillation. So honestly speaking, I don't memorize things. So when you have cosine of alpha plus cosine of beta, I think let's go with this way. Cosine of alpha. Okay, let's do that way. Cosine of A plus B is cosine of A cosine of B minus sine of A sine of B, right? And cosine of A minus B is cosine of A cosine of B minus plus sine of A sine of B. Then 2 cosine of A cosine of B is equal to cosine of A plus B plus cosine of A minus B. All right, so so A plus B, I assume that is alpha. A minus B, I assume is beta. Then what I get, A is equal to alpha plus beta divided by 2, and B is equal alpha minus beta divided by 2. So then cosine of alpha plus cosine of beta is equal to 2 cosine of alpha plus beta divided by 2 cosine of alpha minus beta divided by 2. Okay, good. So here is 2 cosine of sum of the 2 divided by 2, which is k plus k prime divided by 2 times R1 minus R2. Then I have cosine of k minus k prime divided by 2 times R1 minus R2. Good. No need for this one. I just done it for myself. Good. Excellent. So I have 4 eta I0, 1 plus 2 cosine of k average, right? The k average is the average between k and k prime. R1 minus R2 Then the other term is cosine of the difference between the k, which is, I call it delta k divided by 2, R1 minus R2. Okay, so now can you tell me which one is fast oscillating?
Delta K?
Really?
Oh, no,
What is
no,
k?
no, I am not very smart.
No, you are. You are. So k is 2 pi divided by lambda, right? Essentially, and we know that the k and k prime, they are very close to each other. So when there is a difference between the two, then you expect that this value is lower. So delta k is much, much smaller than k and k prime, essentially, and also, of course, k average. True? So this term is slowly oscillating, while this term is highly oscillating. All right? So a small difference between R1 and R2 causes a lot of oscillations on the first term. Well, small changes in R1 and R2 will not cause too much changes to the cosine of delta k divided by 2. Okay? So one of them is something that if I want to do the mathematics k, let's say we are looking at the wavelength of 500 nanometer, which is 0.5 micron, then 2 pi divided by lambda will be 2 pi divided by, okay, 2 goes away, 10 power of 4, it will be 4 pi 10 power of 6, okay? So for this is 4 pi 10 power of 6. All right. Well, if you look at that one, the changes in the k vector essentially will be an order of few hertz, few tenths of hertz or few thousandths of hertz, few hundred of hertz. So that's the reason that this is highly oscillating, this is less oscillating. So, by the way, this is a smart way. And if you do a little bit of approximation, if you assume that the star has a dimension, and then you want to resolve the angle of phi, which is what we want to do, and we know the distance, which is r0, then the entire this term here, with the geometry, if you do a little bit of a geometrical calculation, trigonometry and geometry calculation, you will get that is pi r0 divided by lambda times phi. We assume that the chi is 2 pi divided by lambda, and lambda is the wavelength that you are selecting with the interference filter. Clear? Josh? All right, so that is the scenario. So essentially, by looking at the interference or looking at the intensity over the time, if you have a film there, which is, or a CCD camera, if you look at the fringes, essentially you will get for eta I0, 1 plus 2 cosine of K average of R1 minus R2, which also that can be simplified. I don't want to take care of this. Cosine of pi R0 divided by lambda phi. Okay. What we do, we essentially, if you remember, the difference between these two was R0. I will change this R0 such a way that the fringes disappear or appear. So whenever pi R0 divided by lambda phi is equal to pi, which you have a minimum intensity, then you will understand that phi is equal to lambda divided by r naught. So you know the wavelength and you know the distance of star, and then you understand what is the phi of the star, okay? And clearly that's a brilliant way of determining the size of a star. The problem is this term, because also this term oscillates. I mean, we just discussed about that. And it is not a fixed oscillation, because also we have a lot of factors which we cannot control them. So, I mean, you look at a star, and what you see as the first effect on the star, you will see blinking, right? Which is due to the turbulence, because they look like a point source. I mean, they are not really point source. They have some certain spatial coherency, which you do see the blinking due to the turbulence effect. So you don't have any control on the turbulence effect. That's the reason that people in observatory, they develop a lot of techniques to compensate for the effect of turbulence. And any small changes there will affect this term. And since this term is highly oscillating, it is washing out the interference effect. Although this technique is wonderful, but remember that it works when you have a perfect situation. So that's the reason that most of the observatory, they place them in a really on mountains, because they don't want to have any atmospheric turbulence effect there. So that was the reason that people, they thought about a different way of performing the experiment, okay, and determining the size of star. And that comes a genius experiment developed by Humphrey-Brown, a single person, and Twiss. Okay, so Humphrey-Brown and Twiss, they came out with a brilliant setup, which causes a lot of noises in community, if whether this experiment is true or not, and they got the Nobel Prize for that. Let's look and review what they have done. So assuming that you have these telescopes, which is exactly what we have done, but instead of interfering them together, collect each of those lights by two different detectors. You may say, that's not stupid, because then I will create current. So I have two telescopes, which essentially at that time was radio telescope, by the way. Okay, so I have two telescopes, which these two telescopes, they produce current for me. Current. I didn't know that I'm good at painting. If you call these good. Okay, so this is the detector 1, and this is the detector 2, or telescope 1, telescope 2. They are watching stars, exactly the same fashion that we just discussed that. So one is coming at the K prime, and the other one is coming at K. Okay. So what is the outcome of this? So I have detectors there. What I get here, I get exactly a radiance or intensity of the beam there, right? Do you agree? I get I1. And from the second one, I get I2. What is the expression for I1 and I2? I1 is E1 times E1, one of them is star, which essentially is EK, E power of I, K dot R1 plus EK prime, E power of minus, plus I, K prime dot R1 star times ek e power of I k dot r1. Sorry, yes, r1 plus ek prime e power of I k dot r1. All right. This is what I get. So intensity or irradiance at position of R1 at the time of t is given by this expression. Of course, it has exponential of I omega t with a negative sign, which by the conjugate, they will cancel out each other, okay? We assume that they have interference filter, which they can select specific wavelength, or with the detectors, they can pick up only certain frequencies. Good. So the intensity that I have essentially will be given by a certain coefficient, which is given by detection efficiency, is given by eta. Then what I have ek square modulus plus ek prime square modulus plus ek prime, sorry, ek star, ek prime, then e power of I, let's write it in this way. E power of minus I, k, I k prime minus k dot r1 plus complex conjugate of that term. Agreed? In the same way, you can prove that intensity at R2 also is the same. Is eta ek square ek prime square plus ek star ek prime e power of I k prime minus k dot R2. Note that this is in the position of 2 now, plus complex conjugate. So those are the intensity expressions. So this is one for that one, and this is for this one. What Humphrey, Brown, and Twist they did, they say, okay, now take the two intensity currents and look for the correlation between them. Okay? It's a little bit strange. You may say, how come? I mean, we are looking for the field. How come that we are detecting the field, and after detecting the field, now we are looking for the correlation between them? And that sounds a little bit strange, right? So what they did, they detected the currents. So they had I2 as a function of course, R2 and tau. And then they had a delay electronic, and they look at the correlation between the two. And they had also, of course, I1 of R1 and tau. So essentially what they have looked into, they look at the correlation between I, R1 and tau, T and times R2 and T plus tau. Okay? Or for simplicity, for the time being, assume that even They are coming at the same time. So you are looking for T. Good. So this is nothing more than I1, I2 correlation. The correlation is a little bit higher now. Is not in the field, is in the power of the field. Good. Now let's multiply the two together and let's simplify the equation. What you will get this expression. So I will do that. So first of all, we have to do the multiplication between the two. You will get eta power of 2. Then I get this term multiplied by that term and this term multiplied by that term. Okay, so eta power of 2. Then I will get ek power of 2 plus ek prime power of 2 power of 2. That's the first term. From the second term, what I will get ek power of 2 plus ek power of 2 prime power of 2 multiplied by the product of the two, which is ek star ek prime. I will not write the expression for this. And that will be 2 of this. And finally, I will get an additional term, which is ek star ek prime, and then I will get the expression, which is the product of the two, which is e power of I k prime minus k dot r1 plus I k prime minus k dot r2 plus the complex conjugate of this. Okay, average. So if you do a little bit of mathematics, and of course using the fact that the two, they are independent again, then what you will get this expression. So that will be eta square will be factored out. I can even factor out the ek power of 2 plus ek prime power of 2 power of 2. I can factor out this. Then as an expression, I will get 1 plus 2 ek power of 2 ek prime power of 2 divided by ek power of 2 plus ek prime power of 2 power of 2. And finally, I will get a term which is given by cosine of k minus k prime divided by 2 dot r1 minus r2. Okay. So if we do the mathematics, what we will get essentially in intensity correlation, we get only lower frequency term, which is 1 plus a coefficient of cosine of delta k divided by 2 times delta r, which is based on the calculation that we have performed, this is equal to 1 plus cosine of pi r0 divided by lambda times phi. There is no highly oscillating term. Only lower frequency appears in intensity correlation. So Humphrey, Brown, and Twist, when they did this experiment, it makes us a lot of noise, and they say, okay, only looking at the intensity, someone can determine the size of a star. And that was the reason that they got the Nobel Prize for. In the next lecture, we will derive the quantum formalism for this, and we get explicitly the expression that people they use, and we show that for thermal light also this relation is sensitive, while for the coherent light the sensitivity is less. You will see that in the next lecture. So it's perfect experiment, perfect measurement if someone wants to do it and want to detect even the thermal light, which is what we get it from the star. I don't know how many minutes do we have? Maybe 2-3 minutes? No? I will do that next lecture. But remember, now we deal with another function, which is G2 function, which is related by intensity. I will do it in terms, I will do it in a normalized fashion. So when we deal with this correlation, guys, right? We look at the I1, I2. Now I will write this explicit expression in terms of field creation and annihilation operator, or in terms of positive and negative frequencies. So G2, now of G2 of, I think, tau. Should I go with tau or should I go with R1 and R2? I will go with tau. Okay. It's given by, I have to have two intensities now. It will be E minus, right, of R and T, E minus of R and T plus tau, E plus of R and T plus tau, E plus of R and T. Okay. Denominator is much simpler. I have E of E negative of R and T, E positive of R and T, E negative of R and T plus tau, E positive of R and T plus tau. Okay, and that is the second order correlation function. And if just roughly I want to show to you, this is nothing more than intensity of 1, intensity of 2 divided by intensity of 1, intensity of 2. That's all. Remember that one of them only is at the tau. Okay. And in the quantum regime, we have to replace that with annihilation creation operator. So a G2 function we have a minus, minus, plus, plus. Now what I do, I will just replace it with annihilation creation operator. So the first one would be creation operator of, at the time of T. The other one will be at T plus 2, annihilation operator at T plus 2, and of T, divided by the photon number average, which is essentially nothing more than a dagger a power of 2. Doesn't matter, at t and t plus tau is the same. So that's the reason that I have written this way. So that's a quantum optics formalism of that. So next lecture, what I will do, I will drive the correlation function, the G2 function for 2 different cases. So it will be maybe for 3 different cases: for coherent state, for thermal, and photon number, or Fock state. You can do it even by yourself. So, and we will be using them. I will stop here, and today's course is over.